first talk this morning, as you have seen, was devoted to one of the main topics of this whole program, namely the reductive groups and their representations. The second talk by Radha Kessar will be devoted to another main topic, namely to fusion systems. And so she will give the first talk in introduction to fusion systems. Please, Radha.
Thank you. Thanks, Gerhard. Okay, so thanks very much to the organizers of the program for organizing the program, and to the organizers of this workshop for organizing the workshop. Yeah, so my remit is, from the organizers, is to give an introduction to fusion systems. Now, by now, fusion systems are sort of quite a wide scope. And I have only 2 hours, so I'm going to mostly concentrate on, just the basics, the core notions, and hope to give you a flavor as I go along occasionally of, connections with other areas, so as to why they're interesting. There are going to be other talks. Ellen Henke's talk later will possibly give some connections, and the lectures on block theory by Marcus Linkelmann also, I think, will make mention of the role of fusion systems. And I'll sort of touch upon these aspects just to set the stage, but mostly it's going to be just, what are these things, okay? Okay, so the main thing we need to that we're going to use, it's a totally simple-minded, elementary thing, is the concept of fusion, okay, in a group. Okay, so G is a group, and is to take any element G, little g in G, and then we just, this notation is standard. If you denote by CG, the group homomorphism in G, which sends an element G, U of G to GU G inverse, U belonging to G. This is an injective group homomorphism. Okay, and this is basically going to be our morphisms. They all come sort of from things like this. Okay, and so if you have 2 subgroups Q and R of G, then we can form the set hom GQR just by looking at all the conjugations by elements G of G. So the map, what it does stays the same, but for the domain and codomain to be well defined, we need that the conjugate of G by Q should land inside R. Okay, and you just collect together all these homomorphisms. So you're picking out all the group homomorphisms from Q to R, which are induced by an element of the ambient group G. Okay, okay, and let me just also here write what would be ot G of Q. That is just hom G of Q with itself. So these will be all automorphisms. And this is just CG from Q to Q. And the condition that GQ is contained in R is just saying that G should belong to the normalizer in G of Q. Okay, so totally elementary. And the idea behind fusion systems is just very easy, and it is to discard the group G and just concentrate on these morphisms between subgroups. Okay, and that is it really. And I mean, I guess it's a totally simple-minded thing, but to make it a reality, or to conceive that it should be even done, and to be able to do it, this is all going back to work of Puig. So he started already in the, yeah.
Are you giving this to finite?
Right now, I think I'm not assuming that they're finite. Okay, yeah, so let's assume G is finite, because it will very soon be finite, yeah. Yeah. Good point, good point. Yeah. Okay. Yeah. Yes.
You should probably assume Q is finite, not G, because otherwise you can't do these free amalgam type stuff.
I'm not going to do that. So thank you. I'm going to mention it, but I'm not going to do it. So I'm fine. I'm cool. Yeah. I mean, okay, just to be on the safe side here, for this part, I'll assume everything is finite for this statement, but everything before makes sense. Yeah. Yeah. Okay. So here, G is finite for this one. Okay, right, and so now let's start, to formalize this idea. And so we can start with our first definition. Okay, and now I'm just going to fix forever a finite P group, because I'm really interested in this notion when we are doing, when you're localizing phenomenon at a prime P. Okay, what I said earlier, of course, makes sense globally, but this is where we want to live right now. So what is the basic definition? So what is a fusion system on P is a category. So the objects, let's call it category F, with objects just the set of subgroups, the subgroups of P, and morphisms. So for Q are subgroups, objects in the category or subgroups of P, the morphisms, which we will call Hom F, because there always be group homomorphisms. Q to R is some set of injective group homomorphisms from Q to R, and with composition of morphisms, just the usual composition of maps. So with composition is just composition of homomorphisms. Satisfying, so the morphism sets there should be enough of them in some sense, okay? And so these two conditions are saying that I'm going to write down is that there are enough morphisms. So the first is just that because we have this group, finite group P, on which over which we are considering everything. So all the conjugations from Q to R induced by elements of P should be inside our set, morphism set, and every morphism should be a injective group homomorphism. So I need not write that, I've already said this. Okay, so you should have them all here. And the second is if you have a morphism, in F from Q to R. So if you allow a homomorphism from Q to R to be a morphism in F, then sort of all its descendants are also there. So then you get induced isomorphisms Q to the image, which is again a subgroup of P. So this also belongs to isomorphism in F, and the inverse where you go from phi of q to q, is also in F. Okay, so this is just saying, if you look at these two conditions together, first thing to notice here is that the inclusion from Q to R, if Q is a subgroup of R, is always included, okay, in the morphism set, because the inclusion from Q to R is affected by a conjugation, namely conjugation by 1. Okay? And then if you combine that with this one, yeah, where basically if you restrict, I mean, the way you want to think about this one is that if you start with a morphism from Q to some subgroup, and you restrict the domain and the codomain in such a way that the conjugation, the actual map still makes sense, you're still a morphism in F. That's all these conditions mean. And so here, so we don't have a finite group G. Okay, so eventually, you know, or in the best situation, P is going to be a subgroup of some other finite group G. But this definition does not ask for that. Okay, but the main example of this phenomenon is coming from there. So G is a group, and I'm sure I'm going to stumble again on something of that form, so I'm just going to assume that it's finite. Okay, and P is a subgroup of G, and then you define the category FPG via, again, objects of FPG are the subgroups. And morphisms, so form FP, G from Q to R is just Hom G QR for QR contained in P. And then this is triviality to check that this is a FPG is a fusion system. Thank you. Yeah, thank you. Okay. So, I mean, this is not a very, it's a very elementary definition, and it's not really that, it's a bit flabby, because, you know, you can just keep on throwing every injective group morphism that you like between Q and R, and then apply 2, so throw in all the descendants, and then you get, you know, you can make up a fusion system. Okay? So what we want really is something, class of fusion systems which are a bit more restrictive. Okay? And so that brings us to the notion of saturation. Actually, can everybody read if I write all the way down, or is it better to, should I just avoid this totally? I just push it up, okay. Well, okay, no, I can't very much push it up. This is about it, okay. Just right here and then push up, okay? Okay, just go halfway down. Okay, all right. So, so now saturation. Okay, so before I define saturated fusion systems, we need to do some yoga around automorphism groups. So F is fusion system over a finite group P. So Fs stands for a fusion system. P is always a fixed finite P group. Okay, and so let's consider two subgroups Q and R of P, and then we can define again, as before, sort of aut FQ to be just hom f QQ. And actually, so these are, by definition, group isomorphisms, automorphisms of Q, which are morphisms in F. But by 2, they are actually automorphisms in the category F. So this is fine to call this auto F of Q. They are really automorphisms. Okay, and this is the group. Okay, so from this fusion system, then, for every Q, you're getting a group, a finite group, a group of automorphisms of Q. And now if you look at the axioms for the fusion systems, what do we know are certainly going to be inside this AutoF of Q, the automorphism group of Q, the inner automorphisms. These are just aut Q of Q. And so that's a subgroup of, it's contained inside. Well, it's a subgroup of homp QQ. So that is aut PQ, just to reiterate the notation. And that, by the axiom, first axiom of fusion systems, that is inside aut F of Q. And then as before, that is. Okay, so every inner automorphism of Q is inside the automorphism group of Q in F. And also, so then we can define out F of Q to be aut F of Q modulo in Q. In Q are obviously normal subgroup of aut Q. And so you get a subgroup of out Q. Okay, so again, this is all just very basic stuff, but it's a bit of notation, and you can't do anything really with fusion systems without introducing this notation. Okay. Oh, okay, thank you. Okay, thanks. Right. Okay, now let's, so we have these, for every subgroup Q, we have the aut F of Q and the out F of Q. We need another thing. If you have a morphism, any morphism in F, then we have the automorphism groups. Auto F of Q is isomorphic to aut F of the image of phi of Q via simply you just take an automorphism here and you conjugate. Okay, so it's conjugation all the way around. Okay. And now we make a definition. So with this notation, so you start with a morphism starting in Q. To every morphism starting in Q, you can associate the set n phi, which is a subset of the normalizer in P of Q, such that if you conjugate Cx, when I'm thinking of Cx as an automorphism of Q, okay, to itself, you conjugate Cx with phi, you land inside the automorphism in P of phi of Q. Okay, so what you're doing here is, this is Cx is by definition an element of the automorphism in P of Fq. Now by transport of structure, you're moving into the automorphism groups of F, of phi of Q in F, but you may fall out of the image of aut P of Q. Okay, so what you're doing is you're only taking those x's, which have the property that when you do this transport of structure, you're still an automorphism induced by P. Okay, and so this is sort of important point here. Okay, and so what this n sub phi, well, it's if you think a little bit about it, if x belong to Q itself, then certainly this is going to be satisfied. Then if you look at phi cx phi inverse, well, that is just conjugation by phi of x. Okay, and that, of course, belongs to aut p of phi of q, because it belongs to aut q of phi of q. Okay, just a question of thinking about it for 1 second. And of course, if x belongs to the centralizer in P of Q, then conjugation by x is just the identity map. And then if you conjugate that identity map with anything, you're just going to get the identity of phi of Q. And so you will also be in aut P of phi of Q. Okay, this is just, if you've never seen this before, it's really elementary, but you just have to once sit down and look at it. And so what you get about this group is that, so from this you get that Q, CPQ, is sitting inside n sub phi, and n sub phi is in fact a subgroup of n sub p of Q. Okay? And so to every morphism starting in phi, you have a well-defined overgroup, okay, inside the normalizer in P of Q. Okay? Okay, and then last notion we need here is a subgroup Q of P is F, is called fully F normalized. If the normalizer in P of Q is greater than or equal to the normalizer in P of R, for any R in P, which is F conjugate to Q, i.e. Such that there exists an isomorphism from Q to R inside F. Okay, so in every F conjugacy class, there will be something that's fully F normalized. Okay, and then the definition, the key definition is, I will put it here. So a fusion system F over P is saturated if following holds. So you have two conditions, and they have names. So first is the extension condition. No, let's give it CELO condition. Do this one. Which says that out F of P is a P prime group. Okay, and the second is what's called extension condition or extension axiom. Which says that for every morphism Q, which we might as well think of ending in P inside F, such that phi of Q is fully F normalized. This phi extends to n sub phi. So there exists an extension phi bar n sub phi to be belonging to F, i.e. a morphism starting in F bar, in n phi, i.e. the restriction of phi bar to Q is equal to phi. Okay, so I mean, this the first extension. The C-law condition is, of course, you know, it's fine to absorb. The second one is the really powerful one, and even though it's written as saying that you know there is something else is some other morphism exists, actually, both of these conditions are restricting what fusions you can get. Okay, so the point here is that, I mean, just think of a tower. Okay. So you start with the morphism from Q to P, and then say you can extend it to n phi, and n phi is quite big. It is actually bigger. And then say you can do, for this extension, you can apply n phi again. At the end, you're going to hit an automorphism of P, because yeah. Say supposing you could keep doing this, but then the first condition tells you, well, inside, when you hit outer automorphisms or automorphisms of P, you have a big restriction. You have to lose all P elements. Okay, so that's what makes the thing quite tight. Okay, so let's just see what all of these things mean in our example. So, okay, so here F is FSG, FPG, P less than or equal to G, and then again, I don't have this in my notes, but I'll just make this example for G finite. To not make any more bloopers. So just let's think about what these things are. So Q is equal to P. So what is aut F of Q? It's all the automorphisms of Q which are induced by group conjugation by elements of the normalizer in G of Q. So that is just isomorphic to the normalizer in G of Q over the centralizer in G of Q via the map which sends G to conjugation by G. Out F of Q then will just become isomorphic to NGQ QCGQ. So you mod out the inner automorphisms. Okay. What does it mean to be fully normalized? Well, so what does it mean for this just means that for every G belonging to G, such that Q and, how does it go? Is it GQ or G inverse Q? Yeah, such that Q and GQ are, so both Q and its conjugate by G are contained in P. We have that the normalizer in P of Q is bigger than or equal to in size the normalizer in P of G of Q. Okay. And then the extension axiom, extension condition in this case is just saying that if you think about what out F of Q is, that QCGQ PCGP contains a seal of P subgroup of NGP. Yeah, just and what is the CELO axiom becoming? That becomes, if you just do a little bit of gymnastics again, this just becomes for every R inside P and N every G element of G, such that R is inside both P and GP, and R fully F normalized. I don't repeat what that means in this group theoretic situation. We have that, if you think about this, we have that the P group N sub phi, which I have not written what it is in general, but it's a relation here. So this is the normalizer in G of P of Q intersected with the normalizer oh no, sorry, this is R. Sorry, I can't read. I need my glasses. Okay. Normalizer in GP of R inside the normalizer in P of R CGR. So this is a P group, and you take the intersection with this NPR CGR, and what you want is that it becomes CGR conjugate to a subgroup of the normalizer in P of R. Okay? It's just, you just do it, and if you work through the definitions, this is what you will get. Okay? And if you, once you get to up to this stage, then it's very easy, quite easy, to see that in this situation, if F is FPG, and P itself is a CELO of G, then F is saturated. The extension, the CELO condition is totally immediate, okay? And the extension just is, you have to apply. So being fully normalized in this case will mean that NPR is a CELO of P subgroup of this guy, okay? I have, yes. Excuse me, yes, yes. Yes, sorry. This was the CELO axiom. This was the extension, yes. Thank you very much. CELO and extension. Thank you. Okay, so the extension axiom is just saying, it comes down to saying that if NPR is a CELO of P subgroup of this group, then of course any P subgroup of it is conjugate to it, as well as just CELO's theorem, applied at this local level. Okay, so we get, this is the, the classical example of saturated fusion systems. Okay, but you can drop the CELO condition and still get saturation. Okay, so I'll give one example. It's quite easy, but I think it's quite instructive, so I will give it. So if you're in these categories FPG, and P belongs to this CELO subgroup, then you are saturated. But let's do an example, easy example, to see that you don't have to have P being CELO. Okay, so let's take G to be Sn, and now you take P to be a CELO of P subgroup of some Sm, where M is less than N. Okay, and we think of Sm as a subgroup of Sn just in the canonical way. Okay, and now you consider F. So P is now a subgroup of G, but not necessarily a seal of P subgroup of G. But if you look at this category, FPG, then it's quite easy to see that this is still saturated. Okay, and actually, it's not really a new category, but in fact, it is just F is in fact FP of the smaller group. Okay, so it just takes a couple of minutes to figure this out. Okay, it just means every morphism in here is actually can be induced by something inside here. That's it. Okay, so C-low condition is not necessary, but of course you have to be careful. If you look at P equals 2 and P is a seal of P subgroup of the alternating group, and G is Sn, then Fp of G is not saturated. C-low condition, you just see C-low will fail. Okay, so you have to be very careful. Yeah, with the saturation business. Okay, so now I just take one remark that fusion systems are naturally, and saturated fusion systems are naturally arising from as these categories FPG. But there are other ways to realize them, and that's partly what makes the theory of fusion systems interesting, is that you can find them in other places. So this is just a remark, because I'm not going to define anything here. And it says that you can find fusion systems. So there are other sources of saturated fusion systems. Okay. So one is p-blocks of finite groups. And in fact, it was this example which motivated, to a large extent, Puch to give these axiomatizations. So I should say that this has all been conceptualized by Puch. He gave the original definitions. What I've given here are slight variants of those. Okay, the terminology has also changed. So this is, but in a sense, these ideas are all due to him. Okay, and then a generalization of this is you can have. They arise from so-called p-permutation G algebras. I won't say what those are. Okay, and then these two are sort of quite closely related, 1 and 2. And then you also have topological sources of these things. So for example, p-compact groups also will give you saturated fusion systems. Okay, but nevertheless, we want to hone in on fusion systems that arise from this situation. So we make a definition. So yeah, F is a saturated fusion system over P. Then we say that F is realizable if F is of the form FPG with a G finite group, and P a seal of P subgroup. Okay. So for some G. And if not, so otherwise, we say that F is exotic. Okay, and I will come back to this realizable versus exotic all the time in the talks, but let me just make a couple of remarks here. First of all, exotic SFS do exist. And we come back to that later. Second, you really, if you drop the finiteness or you drop the CELO condition here, you realize everything. So what do I mean by that? So there exist for any SFS, there exists F over P, there exists finite group G, P less than G, such that F is FPG. Okay, this is a result of Sejong Park. Okay, so in some sense, every saturated fusion system is coming from our it is coming from our basic example. It's just that we may not be able to assure that P is a seal of subgroup of G. You can also remove the word saturated. Yeah, I know. Yeah, that's right. You can remove the word saturated, but okay, yes, you're right. But let me just keep it because I really want to concentrate on saturated systems. And also, here also you can remove the word saturated, but I will keep it. For any SFS, there exists a possibly infinite group G such that P is a seal of subgroup. What this means is that every finite P subgroup is conjugate to a subgroup of P. In that sense, we mean CELO with F equals FPG. So in some sense, all fusion systems and saturated fusion systems are coming from the basic example. So there are two different constructions of this given. So there's one by Liris and Stanko, and then there's also a construction by Robertson. Okay, very good. I have 15 minutes. Just trying to see what I should look at. Okay, yeah, I think I will just spend a few minutes now explaining some connections of fusion with classical connections, basically recalling some classical theorems from finite group theory in the language of fusion systems. Motivation. Okay. So some theorems from group theory. So these are just classical theorems. So here, so P is a seal of P subgroup of G in this section, and G is a finite group. And okay, and so these are just some facts. So this is Burnside's, sometimes called Burnside's fusion theorem, which says that if P is abelian, I'll just state them in using fusion systems. Okay, if P is abelian, then FPG is the same as FP of the normalizer in G of P. So this is saying, classically it's stated if you have two elements in an, if you have a abelian C-lobe and you have two elements of P which are fused inside G, then they're actually fused inside the normalizer in G of P. But that's pretty much saying this. Then the Frobenius P complement theorem says that FPG is the same as FPP if and only if G has a normal P complement. So that is saying that G is a semi-direct product of the OP prime of G with P. Then the first of these people to be present in the audience is Globerman's Z star theorem. Okay. And that says that well, you have P equals 2, and if you have Z belonging to Z of P, such that Z is isolated in the fusion system, such that the only F conjugate of F of Z in P is Z, then in fact you get a strong global conclusion. Then the class of Z in coset of Z in with O2 prime of G is in the center. And that's what's usually Z star of G. So that's the fusion theorem. And I should just make a remark here that the analog for P odd holds, but the proof uses the classification of finite simple groups. And I think it's open, and it would be really wonderful to get a classification-free proof of this analog of Z star theorem for odd primes. So open is a classification-free proof. And so there are several people, finite group theorists, who are very interested, I think, in this sort of problem. So Rebecca Waldecker has done a lot of work around this question. And also, there is also the question of whether this theorem can be proved using modular representation theory. Okay, so Globerman's original proof relies on doing modular representation theory of finite groups, and maybe, well, it would be great if one could use those methods to prove this. Okay, then so there are several results like that from finite group theory, but now I want to give a different type of connection, slightly different connection of fusion and structure, and that's for cohomology. Okay, so P is a seal of P subgroup of G. So then standard fact that restriction from G to P induces an injective group homomorphism, injective map, let me just write it like this, from, let's call it I, from the cohomology of G with coefficients in Fp, so mod P cohomology, into the cohomology of P with coefficients in Fp. And all result of Cartan and Eilenberg. So says that they identify the image of this homomorphism, and so they tell you that in fact this is it's the fixed points under the action of F, okay, 8 star P of Fp, where I guess, yeah, I should have said that somewhere else as well. F is always going to be, of course, Fp, G. Okay, so it's not important. I will write down what this means. So this is the same as saying, so this is all alpha belonging to 8 star P with coefficients in Fp, such that, which are conjugation invariant, okay, so which are such that phi alpha phi inverse, no, I need to do this properly, I'm too fast. Restriction from P to Q of alpha of phi inverse is the same as the restriction from P to phi Q of alpha. Okay, so it's not important what these things exactly are, but you just think of F is acting like a group on this cohomology set, and you just take the fixed points. Okay. So what's important, the point I want to emphasize here is that what this Cartan-Eilenberg theorem is telling you is that mod P cohomology is detected, I mean, is determined by fusion. Okay, and so there is a remark. There's a lot in that. There's a much deeper deeper fact coming from, I mean, related to this, and that is saying that in fact, and I will just not state it properly because I don't have the time, but just to give you a flavor, that in fact F determines the P completed classifying space of G up to homotopy. Okay, and there's a lot in this remark because in order to get to this statement is one of the reasons why the theory of fusion systems has been developed so much by Bob Oliver and Ran Levy and Carlos Broto. That was one of the main motivations, and this has a name, so Martino pretty conjecture, which was proved by Oliver, and yeah, so in some sense, you know, but there's a huge amount of work and theory building behind this. So let me just write. So this is the theory of, so you know, uses theory of linking systems, which is started by Broto, Levy, and Oliver. Okay, so I mean, this I will not say any much more about this aspect, but this is really one of the reasons why this stuff became so interesting in the last decade or so. Okay, so now let's go back to, and I suppose Ellen perhaps is going to talk a little bit more about, you know, why theorems like this have been used and continue to be used to prove parts of the classification of finite simple groups. Okay, so now I'm just going to do one topic, which I'm not even sure. No, I think I will not get to the end of it. So I'll just stop here for today and then continue tomorrow.
Thank you very much, Radha, for this nice talk. Other questions?
Am I correct to say that the first time you used P in the definition you get saturated, or was it snuck in somewhere else?
No, no. You don't. It's only for saturation that we use it.
Is there like an analog based on Hall subgroups or something? I'm not saying it's
Yeah. I mean, I think it's a good question, but I'm not sure if anybody's done this with Hall subgroups or some of the groups. Did you guys try something? Yeah, no, it's a very good question because of the, I mean, yeah.
The second question I have is, it seems a bit forced to force P to be a group at the start instead of a groupoid. Because you're not really using anything structurally about it being a group. You know, why not stay in the category of categories, right? Just start with a groupoid P, and who cares if some products aren't defined? Just conjugate C falls through. That feels much less forced, but I imagine, I know that the application is for classification, but less forced, where do you start to need the P group, really?
Well, this thing about do you need all morphisms to be there, or this is actually, it's a very good, I guess your question is, do you want all morphisms to be invertible? But there's also this thing, do you need them all to be in there? Yeah, and that actually is very pertinent because the theory of this centric linking systems, there was one of the big questions when the homotopy theorists got into this business was whether every saturated fusion system comes associated with this gadget called the centric linking system, and whether, if it did exist, whether it was unique. So the solution was given, first solution was given by Andy Chermak, and in his approach, he uses something that he calls partial groups. Okay? I don't know a lot actually about that, but that is precisely the kind of thing where you go away from categories, where you allow all possible morphisms, where you restrict your class of morphisms. I always, whenever he talked about it, I thought, is there something to do with, you know, is it a groupoid or whatever? I never really, no. Ellen says no. But you're right, I mean, you're right, and there's a lot of work now going on these partial groups and related things. So it's an excellent question.
Further questions? Okay, so let's thank